Hi, I'm Dr. T.H. Culhane from Motion Picture Marine's PORPOISE Robotics Program, where PORPOISE stands for Precision Oceanographic Robotics Program on and in the sea environment. And I'm standing with my colleagues here from PORPOISE.
Jonathan Chancellor from PORPOISE Robotics. Carlton Bowman for PORPOISE Robotics.
Orlando Cruz from PORPOISE Robotics.
Andres Reyes from PORPOISE Robotics.
And back in the corner there, looking at the J2 robot.
Zendon Handy from PORPOISE Robotics.
And behind us here,
Easy Money, PORPOISE Robotics.
and what we're looking at here is the Seahawk prototype, which is a surface robotic craft that is made with a space here to mount up to the, if you'll bring it over, to the Sea Perch. So the idea behind this is that the Sea Perch, which is an underwater vehicle, will go inside here, and it'll have two posts, which we have to add to this, which the robotic claws can go down and reach onto and grab onto. So imagine that this is held in place, but we'll do it by posts sticking up because it will never get up this. So imagine that this then is held, and then the Seahawk deploys it, takes it out to a location. It will have sensors on the front that help it to navigate and know where it's going. So ultrasonic ping sensors that act as eyes, infrared sensors that can detect motion and heat. It'll also have whisker sensors that detect touch. And then what will happen is the Sea Perch will be carried by the Seahawk to a location, and then the robotic claws will open and deploy the Sea Perch, which will go underwater with its camera and take underwater photography. It'll sense the temperature, the depth, the salinity, and the environmental pollutants. And when it finishes its mission, it'll record all that via this Massachusetts Institute of Technology, or MIT Sea Perch sensor suite, which goes on the craft, and then it can be recovered, and the data card, which is in here, this little SD card, can be taken out and the data uploaded to Google's DigitalOcean, so that students all over the world are adding information about sea level, about temperature, all the things that we need to know to get through the next century of global warming and environmental pollution. So we're going to be part of a team, a global team. They don't have the boat, though. They've got the Sea Perch and the Sea Perch sensor suite. Our idea was, how do you get the Sea Perch out to those locations in the water to do the data collection? We build a boat. The boat is built out of the same materials as the Sea Perch. The Sea Perch is built out of easy-to-obtain PVC pipe, which is just fixed together, 2 flotations, some zip ties, and then a little motor with an Arduino board, which is a microcontroller. We did the same thing with this. We just had it evolve from the fish state to the amphibious state. So the same skeleton, the endoskeleton that the organism has, just evolved. And now it's just a big skeleton. It now has a skin on it, so we can mount our motors and our batteries. And it's got the same motors. You can see the motors that are there. We've just used the same motors and put them in here. Now, when we use this craft, it's got its own onboard battery. And it'll go forward or backward or turn left or turn right, depending on what we program it to do. Much as this guy, which you're going to build today, is basically a tiny version of this. And instead of motors, it's got 2 wheels. Those 2 wheels are 2 motors. Motor 1, motor 2. Motor 1, motor 2. So it's identical. It's just powering, instead of a propeller, see, the wheel is just a propeller, right? It's just turning the wheel via gearbox instead of turning a propeller. This is actually simpler than this. And then when we press this and turn this on, it does basically the same thing. It either moves forward, or it turns by turning one motor on and one motor off, or it turns the other way. And we're going to put sensors on this. So everything that we do with this can then be uploaded to the program on this board here. See? So there's a motor, there's an Arduino board, that's this thing here. There's a motor controller. Now that motor controller is identical to this tiny chip here. That's the motor controller for these wheels. We can do that because they're tiny motors. So we can just use this tiny chip with a heat sink to get rid of the heat so it doesn't overheat. That metal thing that looks like this, that's a heat sink. It means the heat goes away like down the sink. You get rid of the heat, otherwise it would burn up. On this motor controller here, there's the chip. It's a bigger chip, and because it's attached to this big board, it can dissipate its heat better. But it's almost like, just think of this this board as being identical to that chip, and it's mounted on the same Arduino microcontroller. That's the microcontroller. This is the brain. That chip is the real brain, and then there's places to plug stuff in, and there's a clock there. That metal thing is a clock that keeps it running at a certain speed, a place to plug things in, and some capacitors and resistors and LEDs. So these are the brains. You see that this one, this big chip, is replaced by this tiny chip because things are getting smaller and smaller. This one was made by a robot. This was made by human hands. So when you make it by human hands, you have to have a big place to plug in a chip by your hand. Here, a robot just went psst. So things get smaller and miniaturized because robots are doing it. No human hand could possibly do that. But I just want to show you it's identical. They do the same thing. It's the same brain. Then we're plugging this motor driver with the H bridge, they call it H bridge because it kind of looks like the letter H, doesn't it? Mm-hmm. It's called an H bridge. Follow that? See that looks kind of like the letter H? Yeah, I'll see that? Yeah. So it's called an H bridge. This is also called an H bridge. It's covered up by this heat sink so you don't see it. That H bridge we're going to use exchangeably with motor driver. So when you hear H bridge, think motor driver or just say motor driver. In this case, instead of wiring it with all these wires like I'm doing here to get to the H bridge, it's already got pins, so I just plug it in. Makes it simpler, okay? I can't get it. Who wants to see if they can, without damaging the pins? You don't want to take that risk. Let me take the risks. Okay, so that goes on. Then an example of the sensors that we're going to be using. This is not hooked up yet. These are the eyes. They're not literally eyes. They don't see light. They actually are ears. They are sonar. You know sonar in the Navy? Bing, bing, bing. Dolphins use it. What else uses sonar? Bats use sonar. And the Navy uses sonar. This is sonar. So they're each going to send out a high-frequency pulse of sound that you can't hear, but a bat could hear. And then when it bounces off an object, comes back, and then this logic board determines how fast it went out and how fast it came back, and then it uses an equation to determine the distance. So we know that electromagnetic radiation travels at a certain speed, called the speed of light, 3 times 10 to the 8th meters per second. Sound travels slower than that. Sound travels, I don't know how fast, but it's slow enough that we can have airplanes go faster than the speed of sound. Right? So the sound wave that this sends out travels at a known speed. If it hits Luis and then it bounces back, the computer on the back of this will calculate what the distance was. It'll then report that back to the Arduino board when we hook it up, and it'll tell it, you're getting close to a wall, you're getting close to a wall, and then the program inside that brain will say, when it gets to within, say, 10 centimeters of the wall, turn around, or slow down, or stop, or whatever we tell it to do. So that's going to be mounted here. Problem is, we don't know how to keep it waterproof. If we put it inside a glass bubble, then we have to make sure that the sound wave can get out of the glass bubble. So we have to do some testing on that to make sure it doesn't interfere or it gets the wrong readings. But that'll go up there on the nose. We can put one there. We can put one there. We can put these anywhere we want to. Then, when the boat is on the water, we have to have a way of controlling the boat. And controlling the boat means we got to talk to it wirelessly, and that's what this is for. We're going to put this on top of this, and this is a receiver, and then there's a transmitter, and so we'll be sitting on the shore with our computer, and we'll be able to tell the boat, turn left, turn right, go backwards, send that command wirelessly. If it's received by this receiver, it tells the brain then tells the motors whether or not they should turn left or turn right, or everything that you saw with this. And since people have just come in the room, we might as well demonstrate this little guy. Yeah.
This is Mr. Seitz. This is Mr. Lust. Possibly keep you maybe interested.
Oh, really?
Flowing automatically?
Sorry. Aside from this is an engineering
Robot.
What do you guys do now?
We're working on the Sea Perch. I was just explaining that the Sea Perch program, which the Navy started at MIT years ago. I guess I should go through this.
No, just do it. We're actually in a meeting, so but I just want him to see.
Yeah, the Sea Perch is an underwater, an ROV, remotely operated vehicle that normally is tethered, and then there's a little control box that he's working on there, and the student can stand by the edge of the pool and can go like this and move it. The Navy said that's not enough. We're going to take it to the high school level. It should be something that can be deployed out on the ocean or on a lake. So what we did is we took the Sea Perch and we built a surface craft out of the same materials. So we said, okay, the Sea Perch is built out of PVC pipe. We'll build the surface craft out of PVC pipe. The Sea Perch is not glued, so students can take it apart and put it together wherever they travel. They use zip ties, so we use zip ties. It makes it a little bit wavery, but it works. It works fine on the water. We've tested it. It takes up to 10 kilograms. So it works fine. It's just got normal bottles, 2-liter bottles for the floats on the wings, and a gallon jug for the float in the front. And that displaces enough water, because you know every liter just displaces a kilogram of weight you can put on. So we can get up to 10 kilograms on here. It's got robotic claws so that when the Sea Perch is docked with it, and we're going to put a T here with a pole, so this is not finished yet, it will then grab on to the Sea Perch. And again, it's going to be, imagine that's, I'm not going to do it here. You see what I mean? It's going to be a pole that this grabs onto. And then this thing carries the Sea Perch out to location. We have ping sensors, so sonar, GPS, and accelerometers and navigational compasses we're going to mount. You can then deploy it to a certain beacon or a certain location with dead reckoning. They say that's where your mission is. Then send a remote control via the XP wireless transceiver. Deploy Sea Perch. The Sea Perch will be released by the robotic arms, and then it'll go on its mission. And then using another receiver, either Bluetooth or wireless radio, they will then, by remotely put a camera mounted on the Sea Perch, steer it underwater to collect data. This is the MIT Sea Perch sensor suite, which Massachusetts Institute of Technology is just releasing. We're beta testing it for them. It has a light sensor, so they can measure turbidity. It's got a pressure sensor, so they can get depth measurements. It's got a temperature sensor, so of course they can do that. And then the next revision will have salinity. And they're deploying this to schools around the world now, and the students then send these underwater mounted to the Sea Perch, and when they recover it after a mission, they take out the SD card. There's also a clock, so it timestamps every event. You program when it gathers those events. Then they have a deal with Google's DigitalOcean where students take this data and put it in their SD card reader in the computer, upload it to DigitalOcean, and then it adds to a map that they're doing for real environmental monitoring. They want citizen science.